Greetings. The time, 1665. The place, Europe, more specifically England, more specifically an estate outside of Cambridge. Now in 1665, the Black Plague, which would eventually kill around a quarter of all of the people in Europe, was raging, and so they shut down all of the universities, cut down on transmission rates. And so Isaac Newton had to leave Cambridge, where he was a professor, and go to his estate outside of Cambridge. There he sat under an apple tree one afternoon, as the legend goes, and he sees an apple fall from the tree. Now Newton, being Newton, says to himself, that apple is falling because of the force of gravity. Being Newton, he also could look up and say, you know what? The moon, which is orbiting the Earth, has to have a net force acting on it in order to orbit, moving in essentially nearly a circle. Right? And so, I wonder if that force of gravity, which makes the apple fall from the tree, is the same force that keeps the moon in its orbit around the Earth. Now, you may not think that's too revolutionary of an idea. If I had asked you what force is it that keeps the moon in its orbit, you would all answer the force of gravity. But at that time, they thought gravity was a terrestrial thing, meaning that gravity was only something that occurred on the Earth, that you couldn't extend gravity out to the heavens. And so this was a revolutionary idea. Perhaps this force of gravity actually was more universal. It didn't just take place on Earth, it took place everywhere. Notice, nowhere in this discussion are we saying that Newton discovered gravity. That's often something that's attributed to him that is not true. Galileo knew about gravity, right? Free fall and those kinds of things that we've talked about. And before that even. It was just this extension of gravity, and then, as you'll see here, our understanding of gravity that Newton deepened. Now, what about this orbiting moon? It's kind of an interesting idea. It's called Newton's mountain, and it's how Newton, and modern physicists for that matter, think about orbiting objects. So let me show you a little app I found on the web. What you're about to see is an actual drawing by Isaac Newton in his Principia, and this drawing is called Newton's mountain. So, consider, here is the Earth, here is a mountain, there is a cannon on top of that mountain with a cannonball pointed horizontally. If we shoot off that cannonball, what will it do? Well, since we've already studied projectile motion, we know it'll shoot off in a parabola. If we make it go faster, it'll shoot off in a little wider parabola. Even faster, we get an even wider parabola. But notice something is starting to happen here. Now, the curvature of the Earth is making that object go further than it would if the Earth was a flat surface. So even faster. It goes even further. Now, if it goes fast enough, perhaps it'll miss the Earth and continue to fall, falling around the Earth and hence being in orbit. So this is how Isaac Newton explained orbiting. Objects in orbit are actually in free fall. They are constantly falling towards the center of the Earth. They're just moving so fast sideways that they miss the Earth because of the curvature of the Earth. So it's like projectile motion that never ends. You're constantly falling, accelerating towards the Earth, and by Newton's understanding, because of the force of gravity, you just never get there because you're moving so fast sideways that the Earth curves away from your motion. Watch again. Watch it fall constantly towards the middle of the Earth. There's constantly a force here acting inward. And so again, Newton's great realization was, perhaps this force is gravity. Now, Newton, being Newton, of course, wanted to see if he could describe that force of gravity, the strength of that force of gravity, with an equation. So first of all, being Isaac Newton and knowing his laws, Isaac Newton knew that the force of gravity exerted on the moon by the Earth must be proportional to the mass of the moon. After all, F equals ma. But being Newton, he knew that if the Earth was pulling on the moon with a force of gravity, then the moon would have to be pulling on the Earth with a force of gravity. Now, we actually see that force through the tides, right? That causes the tides on Earth. So the moon is actually pulling on the Earth. And if we look at it from that perspective, the force of gravity exerted on the Earth by the moon must be proportional to the mass of the Earth, since F equals ma. Now, as we've done several times in labs, if the force of gravity is proportional to the mass of the moon and the force of gravity is proportional to the mass of the Earth, then the force of gravity must be proportional to the product of the masses of the Earth and the moon. So again, Newton decided that perhaps the force of gravity that's exerted between the Earth and the moon is proportional to the product of their masses. Now, the next thing. Newton, being Newton, also studied a lot of optics and light, and he figured that the gravitational field created around the Earth must dissipate much like the light does if light comes out from a point source, that it must expand in a sphere. I mean, after all, think of like if you drop a marble or a rock into water, right? The wave that's formed goes out and expands in a circle. Right? Two-dimensional. So in 3 dimensions, it would expand out in a sphere. And since the surface area of a sphere is 4 pi r squared, this is what would happen. If this is our point source, at some distance we'll call re, so perhaps this is the radius of the Earth, right? The area would be a. And, of course, the gravitational field strength is little g. But look what happens if we go twice the radius of the Earth. Now, because this area is expanding in a spherical shape, 4 pi r squared, when we're 2r away, we don't get twice the area, we get 4 times the area. And if the same gravitational field strength is spread out over 4 times the area, it will only be 1/4 as strong. And if we go 3 times the radius of the Earth, we'll now cover 9 times the area, and therefore the gravitational field strength will only be 1/9 as large. So notice here, as the radius expands, the strength of the force of gravity and the gravitational field strength decreases, but not proportional to the radius, but proportional to the inverse of the radius squared. So Newton decided that like light works, like the electric field works, the gravitational field perhaps is what's known as an inverse square function. It decreases with the inverse of the square of the distance between. All right, so r again here is the distance from the center of the Earth to the center of the moon. Center of Earth to center of moon. So if you put that together with the product of the masses, you then get what Newton ended up with, often called Newton's inverse square law of gravitation, which is that the force of gravity acting between the Earth and the moon must be proportional to the product of the masses and inversely proportional to the square of the distance in between. And then Newton took one more radical step. He said, well, if this is the force of gravity between the Earth and the moon, why does this force of gravity have to be only between big things, like the Earth and the moon, or the sun and the Earth? Why can't it be between any masses that are a certain distance apart? So Newton said perhaps all masses have a force of gravity acting between them that is proportional to the product of their masses and inversely proportional to the square of the distance in between. That means tomorrow when you're sitting in class, look at the person next to you. According to Isaac Newton, you are attracted to that person. The more mass you and that person have, the more attracted you are to one another. The farther apart you are, the less attracted you are to one another. So that old saying, distance makes the heart grow fonder? Isaac Newton would say bunk. It's the other way around. And in fact, it's even worse. If you're twice as far away, you're actually 1/4 the attraction, according to Newton's inverse square law of gravitation. Now, this is only a proportionality. So in order to turn a proportionality into an equation, we need a constant. But Isaac Newton actually wasn't able to perform an experiment that was precise enough to figure out what that constant had to be. It took 100 years after Newton before another Englishman, Lord Henry Cavendish, might have heard of him in chemistry class, 1731 to 1810, created an experiment. Here's a diagram of his experiment. Figure 1 of Cavendish's paper on this. This diagram actually is of a device that's the size of a room. Okay, so you would be looking through these little eye holes here. Okay, looking through these little eye holes at what's going on, and those would be like at, standing height. So this is a huge room, and what you have here are two huge lead metal balls. Okay, they're hung from a wire. They're hung from a rod, which is attached to some wires, which is hung up right here. These two rods, So you have these two big metal balls hung up here. Okay, there's a little pulley, string hanging over the pulley, string hanging to outside. If you pull on this string, you can turn this, so you can move these big metal balls. Then there's two little metal balls, which are attached to this wire, which is hanging up here. Now, if these two things are attracted to one another, then these large balls should attract the small balls, which would make this wire twist and make this bar turn. I'll show you a different little schematic of this. Okay? If we measure how much it turns, we can kind of work backwards and see, well, how much force does it take to make it turn through a certain angle? And so we can measure the amount of force it took to make this small ball, little wire thing twist. We can measure the distance in between. We can measure the masses. So we can measure all of the variables in our equation. Here's a little easier schematic, kind of stripped down. So here's our two small masses, right, with a rod attached to a wire. When the big masses are brought nearby, it makes this one twist. And therefore, the masses move closer together. So we can measure their separation, we can measure their mass, and by analyzing the wire, we can figure out how much force it takes to twist through that angle. Now, when Cavendish did this, and did his graphs, and did his analysis, he came up with a constant of proportionality. We call that constant of proportionality capital G, and it is known as the gravitational constant. And it has a value of 6.67 times 10 to the negative 11th and units of Newton meters squared per kilogram squared. Now this is a very complex constant. Last couple of labs we've done, we've had constants of 1 with no units that we didn't even have to remember. You have to remember this one. Okay? 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Now don't get too hung up by these units, because they're really just there to cancel everything out. Notice if you plug this number in for capital G, the two masses would be kilograms squared, so they'd cancel with this kilogram squared. The r squared, the distance between squared, would be in meters squared, which would cancel out with this meter squared. So these would cancel, you would be left with newtons. So plug that in, kilograms, meters squared, kilograms squared, you'd end up with force of gravity in newtons. And then we come to the law of universal gravitation, sometimes known as Newton's law of universal gravitation, which says that the force of gravity acting between any two masses in the universe, not just between massive things like the Earth and the Moon or the Sun and the Earth, but between you and the person sitting next to you, is equal to this gravitational constant times the product of the masses divided by the square of the separation. Now, traditionally, an r is used here. Some books will use a d for distance. Okay, the r is traditional because of the way it was developed. This is the radius of the moon's orbit around the center of the Earth. Okay, it was the way it was developed, but this r means distance, separation in between. Okay, distance from center to center is what we have to look at here. Now, with this idea in mind, let's think about an apple at the surface of the Earth, the classic example here. this apple would have to be being attracted by the Earth. Well, how are we going to deal with that? I mean, the Earth is a big thing. The apple's made up of a lot of little particles. What we could do is we could break the Earth up into lots of little pieces. Each little piece would attract the apple with a force of gravity. So each little piece would attract the apple with a force of gravity. Then we would have to add up all those forces of gravity. Vectorially, of course, since forces are vector quantities. If you add them all up, Newton figured something out, which is known as his shell theorem, which says that a uniform spherical shell of matter attracts a particle that's outside the shell as if all of the mass were at the center. In other words, we can think of all of these millions of interactions between the individual particles of the Earth and the apple as acting like there was one big mass at the center of the Earth that was doing all of the attraction of the apple. Notice the distance between here would be from the center of the Earth to the center of the apple. Now, this is a calculus idea. For those of you that have had enough calculus, it would be an integral. Okay? Now, this part of the story here is why everything that I started out this video with might be a complete and total fabrication. There is no evidence that Newton actually was sitting under an apple tree, saw an apple fall, and said, maybe gravity, that force that makes that apple fall, is the same as the force that keeps the moon in its orbit around the Earth. This story came out well after that time. And it came out when Newton was in kind of a war with Wilhelm Gottfried von Leibniz. Von Leibniz was a German who came out with calculus. And he said, look at this new math, right, that I've discovered. Well, Isaac Newton came out and said, you know what, I've had that in a drawer for decades. I've known about calculus for a long time. I'm the one that's discovered calculus. He even claimed that von Leibniz had plagiarized from him because they used to write letters to one another, and Newton claimed he had dropped hints about calculus in there, and that von Leibniz had taken those hints and developed calculus, so that really it was Newton's idea. And they were locked in this very bitter battle. And so this story may have been something put out by Isaac Newton and his friends in order to fix in time when he would have had to have known his shell theorem, which requires calculus to prove. So in other words, it would say that Newton would have had to have discovered calculus when he came up with the shell theorem, which he had way before Leibniz came out with stuff. So this may just be a story that was put out there in order to win Newton this battle. And this is a really bitter battle over who was the discoverer of calculus. He even had a trial. The Royal Society of England had a trial to try to decide who to credit with the discovery of calculus. Now, Newton won that trial, although it shouldn't be too surprising because Isaac Newton was actually the president of the Royal Society of England at the time. But von Leibniz actually died a very bitter man, very bitter that he wasn't given the credit that he deserved. And depending on where you look it up, which calculus book, some people will credit Newton, some will credit Leibniz, and some will say, well, it was probably some sort of combination of both of them that came up with things. Interestingly, the notation you use in calculus is actually von Leibniz's way of writing calculus. We don't really use Newton's notation anymore. Right? But that's why this big story you hear of Newton and the apple might actually be apocryphal.